In this section, we're going to talk about solving equations. Now, let's understand the difference between expressions, which we talked about in the last section, and equations, which we're talking about now. Expressions look like this. And remember, with expressions, we either evaluate them when given the value of the letters, or we simplify them. Equations look like this. These are all equations, and the prevailing characteristic is that they all contain an equal sign. Now, this equal sign implies that the value of the expression on one side of the equal sign is the same as the value of the expression on the other side. So equations are nothing more than one expression set equal to another expression. Now, with equations, our primary interest is in solving them, and solving them means to find the value of the letter or letters that make the equation true. Now, an equation is a statement of equality. If we want to decide whether 4 is a solution of this equation, then here's what we do. Now, remember, solution means a replacement for the letter or letters that makes the statement of equality true. And to discover whether or not we have a solution, we replace the candidate for a solution with the letter and see if we have truth. Well, when 4 replaces x, we would have 4 plus 3 on the left side. Now, on the right side, we have 7. I'm just going to separate here with a little bar. I could put an equal sign with a question mark, I guess, and because we're questioning whether or not we have equality. But over here, we get 7, and on the right, we have 7. And we know that 7 is equal to 7, so yes, we do have a solution. Now, suppose I change the question a little bit. Suppose I say, is 6 a solution of this equation? Well, we would go through the process the same way. And we're evaluating, you see the expression on each side of the equation. We are evaluating this expression and that expression. And this expression is evaluated by replacing x with 6. So this is 6 plus 3, and on this side we have 9. Well, over here we have 7 in all cases. And 9 is not equal to 7. I can say that like this mathematically. This is not equal to 7, and therefore, no, 6 is not a solution of this equation. Let's go through a couple of others and decide, is negative 2 a solution of this equation? Well, to be able to tell, we replace we replace x with negative 2 on both sides of the equation and evaluate the expression. So we're replacing this x with negative 2, and we replace this x with negative 2 as well. And over here, squaring negative 2, that's negative 2 times negative 2, which is 4. 4 plus 1, oh, that's 5. Now, back over here, we have 2 times negative 2 is negative 4, plus 9. Negative 4 with 9, oh, that's 5. And 5 is equal to 5. 5 is equal to 5, and therefore, negative 2 is indeed a solution of that equation. Is 5 a solution of this equation? Well, to be able to tell, once again, we just replace a letter with the candidate for solution. So we would have here 5 minus 2 squared. And on the right, 5 squared minus 4 times 5, then plus 2. And now we want to simplify. I think it's best to stay on one side of the equation or the other. That is, stay with this expression or that one until we're completely simple. So here, 5 minus 2 would be 3. The amount here is squared, so 3 squared, 9 on this side. Now, I shouldn't really put an equal sign here because I don't know if they're equal yet. That's what I'm trying to figure out. And on the right, I have, let's see, 5 squared is 25. Minus 4 times 5 is minus 20. Notice I'm doing a couple of things at one time in the interest of space here. And then plus 2. Now, collecting 25 minus 20 would be 5, and then 5 plus 2, 7. So let's see, is 9 equal to 7? No, they're not equal. So no, 5 is not a solution of this equation. Now let's talk about solving equations. We talked about solutions, what they are, and how to identify them once we think we may have one. But how do we actually find the solution to an equation? Now, in our past discussions, we have had situations where we've had some simple equations and we have solved them. But the emphasis in those sections was not actually to solve equations. The emphasis was something else. And now our emphasis, we're really talking about a strategy for solving equations. And with the kind of equation we're talking about here, that strategy involves isolation. We are isolating the letter on one side of the equation or the other so that we make the equation tell us the value, the solution. We want the equation to say x equals some number, or n is equal to some number, or some number is equal to y, or something like that. But a letter on one side, a number on the other side, and it's telling us the value of the variable that will make the statement true. Now, we accomplish that. One circumstance for accomplishing that is based upon the addition property of equations. And that basically says this. There are a few ways to say this, but if the one expression is equal to another, then we can take a third expression, a number or a constant or a variable expression, and add on both sides of the equation, you see, and still maintain this idea of equality. So if A is equal to B, then A plus C is equal to B plus C. Now that seems like a non-related kind of idea to an equation such as this, but let me show you how it applies. We're going to take this and we want to isolate the x. You see, we want to make the equation say x equals some number. Now, to isolate x, we need to get rid of minus 5. This says minus 7. We need to eliminate this term, and it says subtract 7. To undo subtract 7, we add 7 on both sides. So here's what we do. We say, let's take the expression on the left and add 7. And let's take the expression on the right and add 7. Because after all, whatever we do on one side, we have to do the same thing on the other side to maintain the balance of this equation. That is, we have a statement of equality. The value over here is the same as the value over there. To maintain that balance of value, we have to do the same thing on both sides. So if we decide to add 7 on the left, we have to add 7 on the right in order to maintain that balance. That's the idea. Now, all we're doing here is following this idea, this addition property of equations. We had a situation like this, where we had the equality of two expressions, and we're deciding to add the same amount on both sides. We're adding 7 on both sides. Now look at what happens in that circumstance. Minus 7 plus 7 is 0, you see. So we have, and I'm going to emphasize what we have over here, x plus 0 on the left, and on the right we have negative 2 plus 7, which together becomes 5. So x plus 0 is 5. Now, the addition property of 0 tells us that when 0 is added to any real number amount, that we get that number. So let's see, x plus 0 would be x. Generally, we don't write this step with the 0 in it. It just emphasizes the fact that these were collected together in a trivial operation. Now, x is equal to 5. We have made the equation tell us the value of x that solves the equation. Now, one great thing about working with equations is that we can always check them. We can check to see if the answer is correct. And let me come back over here and show you how the check works. Check. To check an equation, we're doing what we did over here. We are asking ourselves, is 5 a solution of that equation? So we write the equation. We replace the letter with the number that we find for it, and we evaluate. 5 minus 7 is negative 2. On the right, we also have negative 2. Negative 2 is equal to negative 2. A true statement, therefore 5 is indeed a solution of this equation. Let's solve some others. Now, remember that this is an isolation process. What we're trying to do is undo some operation that we see in order to isolate a letter. So here we see x plus 8 equals 5. We want to get rid of the plus 8. To get rid of the plus 8, we see add 8. Well, we subtract 8 to get rid of it. So it's x plus 8 minus 8. You see, we bring down the expression on this side and show what we're going to do to it. We bring down the expression on the other side and we do the same thing over here. Now the 8 minus 8 go out and we're left with x. And on the right, 5 minus 8 is negative 3. And again, we could go through the process of checking here. We could even check by observation when they're simple. If x is replaced with negative 3, up here we would have negative 3 plus 8 oh, negative 3 plus 8 is 5, 5 equals 5, a true statement, therefore a correct solution. In this one, the letter is on the right side, but that doesn't make any difference. We're isolating on either side of the equal sign, so we're going to eliminate this minus 2 on the right side, and we do that by adding 2 on both sides. So we would write 3 plus 2 on the left, and then y minus 2 plus 2 on the right. You see, again, it's this idea that we take the expression over here and show the addition of 2. We take the expression over here and show the addition of 2. So we're doing the same thing on both sides, which is very important. 3 and 2, 5 on the left, and on the right, the 2's go out, so we have y is equal to 5. And once again, if we replace y with 5, we have 5 minus 2, 3 on the right side. 3 equals 3, yes. So this is a correct solution. When fractions are involved, we can use the same strategy, it turns out. And when the fractions are simple, it's very easy to use the same strategy. For example, here we are trying to isolate the t, so we need to eliminate the 5/7. And to do that, we'll subtract 5/7 on the right. But if we subtract 5/7 on the right, we have to subtract 5/7 on the left. So we have 2/7 minus 5/7 equals right side minus 5/7. Now, we could use a step here to put 5/7 minus 5/7 next to one another in order to see that they kind of add one another out. But it's fine if we say 5/7 minus 5/7 would be 0, and what's left on the right side is simply t. Now on the left, here's where all the action is occurring. We have 2/7 minus 5/7. Now we have common denominators, so we collect the numerators, and here's what's really going on. We have 2 minus 5 over 7, you see, since we have those common denominators. And 2 minus 5 is negative 3, so this is negative 3 over 7 is equal to t, or negative 3/7 is equal to t like this. Now we'll see another way to deal with fractions in equations a little bit later, but this is a real nice way to take care of the situation, especially when we have common denominators. Consider this equation. If we're solving x plus 3 equals 9, we'd like to isolate the x on the left side of the equation. So to clear the plus 3, we subtract 3 on both sides. So we write x plus 3, subtract 3, write 9, subtract 3. The 3's add out to give x, and 9 minus 3 is 6 for the answer. Now we said that the basis for solving equations like this is the addition property of equations, and that means that we can add the same amount on both sides. But wait a second, we're subtracting the same amount on both sides here. So do we need to introduce a subtraction property of equations? Well, not really, because we can think of this in another way that allows us to extend the notion of the addition property. That is, this means the same thing as this. Suppose I have x plus 3 and I add negative 3. You see, 3 plus negative 3 is the same thing as 3 minus 3. So I'm adding a negative 3, and it's equivalent to subtracting 3. So we don't really need to introduce another property, because an extension of the idea of adding will allow us to do that. Anyway, I just thought I'd mention that because you might be questioning the idea of subtracting on both sides. Let's talk about another kind of equation, or we're going to talk about another kind of equation in just a moment, but we need the notion of reciprocals for this one. Now, reciprocals are just fractions that are flipped over, and we've seen them many times when we divide fractions. You know, we change the division problem into one where we multiply by the reciprocal. So 2/3 and 3/2 would be reciprocals. 1/5 and 5/1 would be reciprocals. 7 and, well, what would be the reciprocal of 7? 7 can be thought of as 7/1, so 1/7 is its reciprocal. Now, the interesting thing about reciprocals and the way that they're useful in solving equations is this, that when we multiply a number times its reciprocal, the result is always 1. That is, if we're multiplying 2/3 times 3/2, we get cancellations all around. The 2's cancel here, the 3's cancel here. So what's left is 1/1 times 1/1. Well, that's simply 1. And 7/1 times 1/7, you can see the cancellations, and the result would be 1 if we were multiplying. Same way here. So let's just keep that in mind as we get into the next group of equations. This group is going to be solved using the multiplication property of equations, which basically says that if you have an equation, if you have one expression equal to another, then you can take another number, you can take a number or a variable term and multiply it on both sides, you see, and maintain your equality. And what this allows us to do is to multiply the same number on both sides, you see, of an equation. That's all that there is to it. And a kind of a trivial situation involving multiplying on both sides is when we have a 1. A times 1 is equal to A, or 1 times A is equal to A. Now let me show you how all this comes into play. Suppose we have 2/3 x equals 8. Our concept for a solution is to make the equation tell us the value that will make the statement true. And to do that, we'll clear the coefficient, the numerical coefficient of x. Now notice it's 2/3 times x. And one way to clear this fraction is to multiply by the reciprocal of that fraction. So we could do this. We could just introduce a factor over here, which is the reciprocal of what we see. Now, does it make sense that if we multiply by 3/2 on the left, we need to also multiply by 3/2 on the right? So we're multiplying by 8. I'm kind of raising the 8 because I want to think of the 8 as 8/1, you see, in order to get that cancellation correctly. But the notion over here is that, all right, we're introducing a factor. We have 2/3 times x here. We're introducing a factor. We're thinking about it like this, using our associative property of multiplication, you see. We think of it like this, and 3/2 times 2/3 is just simply 1. So this is 1x, and by that multiplication property of 1 times x is simply x. And we generally won't write this, but I think it's important to realize that there is some basis for us performing this kind of operation. We would probably just say, oh, this is 1x, and generally coefficients of 1 are not written, so we would have x. And on the right, we would just perform the operation. 2 into 2, 1, 2 and 8, 4. 3 times 4, 12. So x equals 12. And again, we could go through the check process. We could replace x with 12. We'd have 2/3 times 12. Now imagine 12 right here. If this is 12 and we have 3 down here, the 3 and the 12 cancel. 3 and the 3, 1. 3 and the 12, 4. 4 times 2, 8. So we'd have 8 over here. 8 equals 8. Yes, a true statement and a correct solution. Let's go through it again. Now with this, we have a coefficient which is an integer rather than a regular fraction. And in such a circumstance, we can think of a strategy for solution really in two ways. One way is like this, is to think, well, let's multiply on both sides by the reciprocal of this. So I would be thinking, what's the reciprocal of -4? Well, it's 1/4, or -1/4. So I would be multiplying by -1/4 on both sides. Okay, so I'm doing this. That's what I'm thinking about. But if I multiply by -1/4 on the left, I have to do the same thing on the right. And now everything will come out fine. Remember, this is -4/1, so we get that cancellation of 4's. And negative times negative is positive. So we have positive 1x, or simply x. And on the right, the 4 and the 4 goes 1. 4 and 24 goes 6. So this is -1 times 6, -6. And again, we could check it if we'd like. Well, let's do that. If x is -6, we have -4 times -6. Negative times negative, positive. 4 times 6, 24. 24 equals 24. Truth, and therefore a correct solution. Let's look at another way to approach this. That rather than thinking of multiplying by a reciprocal here, I think what I'd rather do, and in the long run it's a little faster, I think, is to simply realize that dividing by -4 is the same thing as multiplying by -1/4. I mean, after all, if we were multiplying by -1/4, when we multiply 1 times this, you see, we would get that. And if I let this minus sign float into the denominator, let me go through and show you what I'm talking about. That if I'm multiplying these two, let me rewrite to make it a little more obvious. All right, this is the reciprocal of that. If I multiply these, I get negative 4x over negative 4 times 1 is negative 4. You see, I'm not canceling because I want to show you something, but it's that we have this, and we actually have a division by negative 4. So I could think of, rather than multiplying by the reciprocal of this, I can think of just dividing on both sides by negative 4. And I think that's a little bit easier. So here's the way we would think about it. It still follows this notion of the multiplication property, you see, of equations is division, because division can be defined in terms of multiplication. But here's the way we think about it. We say, okay, I'd like to eliminate the negative 4, which is multiplied times the x. To eliminate that multiplication, I divide. So I'm going to take the left side and divide by negative 4. But if I divide by negative 4 on the left, I need to divide by negative 4 on the right. And now the negative 4's go out, and I have 24 divided by negative 4. Oh, that's negative 6, as expected for the solution. I kind of like this way better than the other way, but either way is fine. And when you have fractions involved, like this problem right here, it's important to know that we multiply by reciprocals, that is a good strategy. Because here we would be thinking, gee, how can we eliminate that 3/4? Oh, easy. We multiply by its reciprocal, which is 4/3. So it's 4/3 multiplied on the left, and 4/3 on the right. Now I'm going to emphasize the notion that this is a fraction by writing it over 1 like this. Well, we would probably write it like this, but when we look at it to multiply, we're thinking of it like this. You see, we're reassociating in our heads, and multiplying a number times its reciprocal gives us simply y. We get 1y, which is y. And on the left, we see the cancellation, 3 into 3, 1, 3 into 9, 3. Don't forget about the minus sign. This is 4 times negative 3, negative 12 for the answer. Now here's one where we have a little bit of manipulation to do before we go through the process of dividing on both sides or multiplying by the reciprocal. This says on the left we have an expression that we can simplify a little bit. And occasionally we need to do that before we introduce another strategy. 6z minus 8z. 6 minus 8, oh, that's negative 2z equals negative 5. Now we go through that process of dividing by this numerical coefficient. So we'll show that we're going to divide on both sides by the coefficient negative 2. These cancel out as expected, so we find z to be negative divided by negative is positive. This is 5 over 2. Well, gee, I might write this as a mixed number. 5 divided by 2 is 2 with 1 left over, so this is 2.5. Here's a word problem. Now, we've solved word problems in the past, and in fact, we've solved word problems similar to this one. We've had discount problems, markup problems, and such things, and this involves that kind of idea. Suppose we have a store and the sale price for a pair of slacks is $44. This is a discount of $16 off of the regular price. Use the formula S equals R minus D. Now, S is sale price, R is regular price, D is discount, to find the regular price. Now, all we do in using a formula is you write the formula down in the first step and replace within it in the next step the information that you know. S is the sale price. It says the sale price for a pair of slacks is $44. You see, so replace S with 44. There's no real mystical understanding that we need here. We're given the formula. We don't have to invent one for ourselves. And that's the easiest situation of all. Now, the regular price, the R, is what we're looking for. Then minus the amount of the discount. Let's go look for a discount of $16. Okay, so the discount is 16. You see, and now we have built an equation from the formula is an equation, but we have built it with numbers involved in it. We have a letter to solve for, and to solve for the letter means that we're going to isolate that letter. To do that, we'll undo this minus 16 on the right. Well, to do that, we'll just add 16 on both sides. So we have 44 plus 16. And then on the right, we want to show the addition of 16. These add out, leaving R, the regular price, and then collecting these two, we find that regular price. Let's see, 6 and 4, 10, 4 and 1, 5 and 1, 6, 60. So $60 then is the regular price for these slacks.